We will see now the impact of the drain current. So I will make a cell with this NMOS width, and I'll take one NMOS only. Which NMOS? The standard threshold. See, this is NMOS width. I show you a few parameters now. Time has come that we should start discussing. See, there is given a length of the MOSFET 45 nanometer, finger width and total width. These are the same. When I'll tell you about the layout of the transistor, then you will see, because when I create the two finger NMOS, it means that my width has gone doubled, right? Three finger means width has gone three times, but I can uh, take my width the way the total width. It is not important that I should take the multiplier only. I can take any value of the width that I require. These are the other values. What is the gate connection? Whether you want to go to connect with gate at top, bottom, or both. This is for the layouts. With you want to use DFM rules? Yes or no? What is the metal width at source and drain? This you can see. You can change. Then there is body type. This is required when you want to make the layout that you want integrated or detached. This is your this in particular um, the body of the transistor, whether you want it to be integrated within the layout or you want it detached and you want to create it separately in the layout. So this is again the layout process. These other values, that source diffusion resistance squares, drain diffusion resistance, these are the values which are related with the layout and your post layout simulation values. So these cannot be changed in pre simulation process. These are the similar values. So in all these things, because these most of these values are manufacturing based, therefore there is only one thing that you can change in this case. This length you will not change because you are working in 45 nanometer technology node. If you change the length, you will not be able to simulate your transistor. That will again become a problem for you. So what you can change is, the only thing that you can change in your MOSFET is the width of the transistor. And what is the impact? See, in this GPDK file in Cadence, 120 nanometer is the default width. This is the minimum width. You cannot take anything below it. So I'll take so I'll go to analog library. I'll seek a ground. Then in analog library, you will seek a VDC. Let us take the value of VDC X. View the symbol type. How do we create the symbol? There you have your single NMOS with a voltage to gate and a voltage to drain, When you give similar voltage at gate and drain, means you are running your transistor in saturation. And if you wish to see the DC characteristics of it, we can show it. How do we see the DC characteristics? Let us do the ADL. What is the process? You will go to the DC simulation. You will see this point. You will take component parameter, select the component, take the component of DC voltage. You want to start from 0 to go to till X. Okay, you need the value of X. Let me give the value of X 0.8. Now it will pick. Okay, and I give this value as Y. And your this ADI will ask for the another value, that is Y. I'll give Y 0.8 again. Now what is the output I require? This is your drain current. This point, when you need to take the current, you click on the node. This is your drain current. Now, if you take the DC characteristics, you see, this is the DC characteristic of NMOS, right? What is the maximum value of the current? This is 19.6 microampere, right? This is the, remember, this is a drain current of NM0 transistor. Now I will take, please see this, I will take another transistor. Here, and I will connect its drain with drain, means I'll keep the drains on the same potential. I'll keep the source on the same potential, and I'll keep this gate on same potential. So everything is created, everything remains the same. It is saying that यहाँ पे connect कर दीजिए. Okay, so in output, I want to take now this drain current of NM2, and I'll take the width of this transistor, not 120 nanometer. I'll take it now 240 nanometer. I'll double the width. The previous one was NM0. Now it is NM2. Now I'll simulate it. Okay, so it is saying that you haven't saved it. Now simulate it. Not the both. Now see, this is red one is NM0 and green is NM2. NM0 has the width of 120 nanometer. This has 240 nanometers. So what is the maximum current here? 19.6 microampere. What is the maximum current here? 36.773 microampere. You please see the change in current. However, the point that you should see or notice is this, that despite this, the threshold voltage remains the same. Can you see the point that I marked? I use some other ink. You see this point. They are picking up from the same point. The threshold voltage remains the same, but this takes this path and this one is taking this path. This is 120 nanometer width. This is 240 nanometer width, right? Now let us do the parametric simulation of one MOSFET so that we can see. Let me change if the parametric simulation is possible for. Now I'll take only this NM0 and I name its width to Z meter, right? And now I'll do the parametric simulation. Z is by default 120 nano. If I run it, possible. Okay, right. We are having it, so means we can do that. Now I'll go to the parametric simulation. I'll take the variable Z and I'll use the value 120 nanometer to 600 nanometers. How many values I can see? I'll take 5 steps. You see, not picking. Okay, so it is not picking the parametric simulation. I'll show you the other values of Z. For this value of Z, for this particular value of Z, 120 nanometer, it is showing the maximum current 19.6 microampere. If I change this width to 360 nanometer, the current is 52 microamperes. So it means that whenever you keep on increasing the width of the transistor, the current in it increases. So question is, what I'll do by increasing the current? What is the advantage of it? Why I'm doing this at all? I'll show you the advantage of it. Let us come to the previous example that we have done, this inverter. You see this inverter that we have done in starting of our workshop. Then we use the ADL. In the ADL, I have taken a few values. Okay. You see, these are the certain values. Now I'll find the delay and the power dissipation, right? For the power dissipation, what I need to do is save all, take these values, simulate it. Now this is the power dissipation. Now I'll take the delay. This we have the delay, right? So now we'll calculate the delay and power of the circuit. Now see, the power consumption is 6.585 nanowatts and the delay is 36.39 picoseconds, right? Now what I'll do, I'll change the width of the MOSFET. I'll take from 120 nanometer to 240 nanometer. And when I'll simulate it, the power consumption is 9.22 nanowatts and the delay is 33.59 picoseconds. Now let us see what is the reasons, what is the analogy, what is the concept, what is why this is following this trend. The previous value, this is the value with 240 nanometer width of NMOS. What was the value with 120 nanometer width? The value was 6.585 nano, and here the value was 36.39, right? This has delay has decreased, so it has improved. Power consumption has increased, means it has gone worsened. So what is the reason? Let us simplify the concept behind this. The concept is that you have taken the width from 120 nanometer to 240 nanometer. ID is directly proportional to the width according to the formula. You have increased the width, so ID probably has increased. When ID increases, the power dissipation is V cross I. In your inverter circuit, this V is fixed at 0.8 volts. Because V is fixed, you have not changed the V, means if your power dissipation has gone from 6.585 to 9.2285, means your ID has increased. Now, any doubts on this? Simply, you have increased the width. Because of increase in width, the drain current increases. Because the drain current increases, so the power dissipation increases, V cross I. And when the power dissipation increases, you can see it is visible in your results. Now, let us extend this concept. In a particular MOSFET, your something you give in the input and something you get at the output. In this case, the output depends on the speed of electrons. or number of electrons. Your current has gone high because you have increased the width. And because of increase in width, the current is high. Because the current is high means speed of electrons is higher. Because the speed of electron is higher, that is why the delay from input to output reduces. That is why your delay has come down and power dissipation has increased. Now, please ask if you have any question. I'll give you one more pointer on this. Even if you check leakage, the leakage also increases with increase in width. Because the effective drain current is increasing. That is why the leakage current is also increasing with increase in width. Now, you please ask me if you have any question on this, because this assumption will go on and on when you will keep on making further and further projects in your digital VLSI. Right? Please ask if you have any doubts on this matter. Ashnu is asking, sir, length reduce होगा तो current increase हो जाएगा ना? Ashnu, आप किसी भी MOSFET के अंदर length change करते ही नहीं. You cannot change the length. See, there are libraries in your MOSFET. When you work on Cadence, na, there are certain libraries. See these libraries. This is GPDK 45 nanometer, GPDK 90 nanometer. So GPDK 45 nanometer means all the devices that it will give you will be of 45 nanometer length. So you cannot change the length. If you'll try to change the length, then the trouble will be that you will not be able to use this library or you cannot use the simulations. And how these lengths are decided. There are two questions that I keep on getting from you guys. The first question is that the question I usually get, that why length is fixed. Second question is, sir, you keep on taking this value, input value 0.8 volt, 0.7 volt, 0.6 volt. Are these arbitrary values? Or you take this with some assumption? Let me give you the answer of both questions. The first question is, this whole library, this GPDK 45 nanometer, the model file is created after the assumption of fabrication. If you see this very carefully, where it has gone? Yes, I have shown you this. You see, there are certain values which are given. What is the drain diffusion resistance square? What is the drain diffusion periphery? What is the left source to drain length? What is the source diffusion this? What is the right source to drain length? What is the hot electron degradation? What is the SCB, SCA? These all values are dependent upon when certain library is given to you. Suppose some company is giving you 45 nanometer library. What that company wants, that in 40 for creating 45 nanometer length, we have these much parameters. Now you create a circuit for us. What you can do is, you actually know that you have only one thing in the MOSFET that you can change, that is the width, because length and the other parameters are totally dependent on the fabrication. You cannot change the fabrication process. So this 45 nanometer length has been decided by the fabrication process. That is why you cannot change the length. So the answer to your first question is that why this length cannot be changed, because this is dependent upon the fabrication process. You cannot change the suppose you cannot change the COX, oxide capacitance. You cannot change thickness of oxide. These all are the fabrication based parameters. If we'll get time, one day we will talk about this fabrication process. कैसा होता है fabrication process? For example, एक MOSFET हम लोगों ने create किया. We have created a MOSFET. in this MOSFET, I'll show you the power of fabrication. You talk about LVT, SVT, and HVT. How these VTs are decided in a MOSFET. Let this be the structure of the MOSFET, right? There you have SiO2, and on SiO2 you have a metal from where you give the voltage. Now this gate voltage actually decide that after how much voltage the electrons will be attracted and channel will be formed. Now you tell me one thing. If I make this SiO2 region thick, will the gate voltage required be higher? Or if I make this region thin, then the gate voltage required will be higher. In case of thick SiO2 and in case of thin SiO2. In which case, the channel will form early. Just guess. I repeat my question again. I have a MOSFET. In this MOSFET, I have these two P wells, N wells. And on this N well, here you have a layer of SiO2. Here you have a gate. What is the process? That you give some gate voltage, and this gate voltage attracts the electrons and form the channel over here, right? When the gate voltage required will be higher, if you make the SiO2 thick or if I made SiO2 thin, when the gate voltage requirement will be higher? Ashnu says when it is thin. Anyone else?
So when we make SiO2 thick.
When we need SiO2 thick, if SiO2 is thick, then you say that this gate voltage required will be lowered. Low gate
Higher.
voltage is required. Achha, gate voltage required will be higher.
Yes.
If SiO2 is thick, then gate voltage required is higher to form the channel. And when SiO2 is thin, then gate voltage required is lower to form a channel.
Yes, sir.
Everyone, is it the same case? Thin में channel जल्दी form होगा. अच्छा. Anyone who has a different point of view? अब देखो. Now you see how the fabrication impacts it. If you use dry oxidation, if your industry has a dry oxidation, then this SiO2 layer will be thin. If you have wet oxidation, then this will be thick. So the thickness of SiO2 depends on the kind of oxidation do you do in your industry. So is your threshold voltage. Threshold voltage is what voltage? The voltage on which channel is formed. So therefore, your threshold voltage is something that actually depends on the fabrication process, that your SiO2 is thick or thin, right? So there are many parameters in your MOSFET that depends on only the fabrication process. And only one thing that you can change during the fabrication is the width of MOSFET, right? So the question is that not only length is fixed, but all the parameters that I use in my MOSFET are fixed except the width. And the point is, when I increase the width, the drain current increases. When the drain current increases, the power dissipation increases. When the drain current increases, the delay between the delay in the circuit reduces, that comes down. Okay. So the other thing, what is important, the other important thing to understand is that Sir, do you take these arbitrary values, or how you take this 0.5, 0.4, 0.6? Please understand this also. If you are using 90 nanometer technology node, or you are taking 180 nanometer technology node, or you are taking 45 nanometer technology node, this 90 nanometer means you will work on 0.9 volt onwards. Actually, these are defined in the process design kits. These are defined in your this PDK that you get. In 180 nanometer, you usually work on 1.8 volt. This also, it can be seen from here. Divide 90 by 100. This is 0.9. Divide 180 by 100. This comes 1.8. Similarly, divide 45 by 100. So this works on 0.5 volts onwards. That is how we decide. And the maximum voltage that we go in 90, this 45 nanometer is 1.1 volts. In this case, probably, I don't remember it, probably 1.5 volts. In this case, I don't remember what is the highest voltage, but we start with 1.8 volts. These are not the arbitrary values. These are the values. Again, this depends on the company which is fabricating your MOSFET. That fabricating company gives you this GPDK. This GPDK, what is the meaning of GPDK 045? It means generic process design kit. Generic means this process design kit. This kind of a MOSFET has been created for your experimental purpose only. This is generic. Otherwise, if you need to create a MOSFET, actually, suppose you are working with TSMC, so TSMC has its own model library. If you are working with SCL Labs, they have their own model, their own PDKs. Any company you work with which is fabricating the MOSFET, they have their own PDK. This GPDK is the generic process design kit, generic PDK, to make you understand that how to do experiments, how to do simulations, how your industry work, how to understand the fabrication of transistors, right? So these are the basic things that you need to understand about. So we have seen about today we have learned about the width. Okay, one more parameter that I want you to understand today, and that parameter is called the threshold voltage. Now, if you see carefully the formula for threshold voltage, let me open the book. What is the formula for threshold voltage? It is this particular formula for threshold voltage is used for understanding how your threshold voltage works. So threshold voltage formula is, if you see this VT naught, this is equals to phi GC minus 2 phi F minus QB naught divided by COX minus QOX divided by COX. Now the question is, what is phi GC? Phi GC is the work function difference between substrate and the metal. How, see your MOSFET, in your MOSFET where your gate is connected. When your gate is connected here, you see SiO2, you have this dielectric, and this is your metal. So there is a, and there you have the substrate. So phi GC talks about the work function of your substrate minus work function of your metal, right? And then your 2 phi F. What is phi F? Two phi F. 2 phi F is actually, you say that is it is the, when you talk about the externally applied voltage, the gate voltage from here, you see that this gate voltage must be changed to achieve this inversion over here so that you can create the channel. Now we need to place, when we talked about this criteria, that initially we have the layer of holes over here. Then we create the layer of electrons. Means we do the process of inversion. We studied in our initial lectures. To do this to the 2,5F, we need this. This is called changing the surface potential. This 2,5F relates to. One second, let me settle it. This 2,5F relates to externally applied gate voltage that will be changed to achieve the surface inversion to change the surface potential by 2,5F. So that is a 2,5F. Now, if you talk about this QB naught, what is QB naught? QB naught is this is the depletion region charge density. When there is no the holes goes here, you have the depletion region here. There is no charge in depletion region, but minimum charge is called depletion region charge density, and this is the oxide capacitance. Then there is oxide charge, oxide capacitance. If you see this carefully, there is no parameter that you can change manually. In the whole formula for this threshold voltage, there is no parameter that you can change manually. These all parameters depend on your manufacturing of MOSFET. That is why your threshold voltage depends on the threshold manufacturing. And that is the reason the threshold voltage for all PDKs is different. Right? So I'll stop here and I'll leave you with all this process only. We'll meet again tomorrow. We'll revise it and we'll see that how these all the things will help me to create a particular project or the memory. Right? For today, that's all from me. If you have any queries, you can please put it to the WhatsApp group. I'll be happy to reply any of your query. Right? The meeting is about to end and we'll have to stop here. Tomorrow I'll start with this threshold voltage only. Till then, good night, dear. Good night, all. See you tomorrow.